Okay, so in this lesson, we're going to use the first derivative to test to determine if a function is increasing and decreasing and find local max and local mins. In the next video, we'll look at concavity and points of inflection. As I've said before, this unit was really important before calculators, and we had to sketch functions without a calculator. However, this is still important because this is one of the most tested items on the AP exam, and the AP exam, most of the AP exam is without calculator. So here's some obvious definitions that we've already sort of hinted on, and we're just going to put into words. When a function is increasing, its derivative is positive. When a function is decreasing, its derivative is negative. The first derivative test says this. We've already talked about a critical number is found when the derivative is either 0 or undefined. So if we take the derivative and it changes from a negative to a positive at that critical number, then the function has a relative min. If we take the derivative and it's 0 at that critical number and it goes from positive to negative, then there's a relative max. If the derivative is positive on both sides or negative on both sides, in other words, if there's no sign change, then the critical number is neither a max or a min. Let's do an example. Most of you could sketch this function without calculus, but let's just use calculus to sketch it. You know this is a quadratic function, and it has a vertex, a relative min vertex. But let's use calculus to determine that. So the first thing we want to do is take the derivative. Then we want to find the critical numbers. Remember, the critical numbers occur when the derivative is either 0 or undefined. Since 2x plus 8 is never undefined, we have to find when the derivative is 0, and that is x equals negative 4. Once we have that critical number, we're going to take that value and plug it into the derivative. So we're going to evaluate the derivative at negative 4. We're going to take values slightly to the left of negative 4, so let's say negative 5, and evaluate the derivative at negative 5, and we find that we get negative values because negative 5 times 2 is negative 10, plus 8 is negative 2. If I take a number greater than negative 4, let's say negative 3, and I substitute it into the derivative, I get negative 2 times 3 is negative 6, plus 8 is positive 2, so those numbers are positive. So I can see that my derivatives go from negative to positive, and therefore there is a local minimum. The function is decreasing from negative infinity to negative 4. It's increasing from negative 4 to infinity. And because the derivative went from negative to positive, it is a local min. Now notice I used this little visual to help you remember that it's a min. My slopes were negative, they went positive, and that will create a minimum. And the value of that minimum is found by substituting negative 4 into the original function. So we say this has a local min of negative 6, and it occurs when x equals negative 4. Okay, so here's our second example. Once again, we're going to find the derivative of this function. We're going to have to use quotient rule. Factoring out a negative x. So we see that the function, the derivative is 0 at x equals 0 and x equals negative 6. However, x equals 6 is the only critical number because at x equals 0, the original function is undefined. X equals 0 is not in the domain of the original function, and therefore it cannot be a critical number. So now we're going to do our sign chart, and remember we're going into the derivative. We're going to take negative 6 into the derivative, and we see that to the left we get negative numbers and to the right we get positive numbers. Now, I did evaluate numbers to the left and to the right of 0. And notice at 0 we do go from positive to negative. However, that is a point of discontinuity and therefore not a critical number. Although the values are changing, between -6 and 0 you have positive slopes, and after 0 you have negative slopes. It is not a min or a max because the function does not exist at x equals 0. So when I want to know what the local minimum is, I look at what's going on at -6. So I see the function is decreasing from -infinity to -6. It's increasing from -6 to 0, and it's actually increasing from 0 to infinity. But we say that because the derivative went from negative to positive at -6, there's a local min at -6. And that value of that local min is -1/12. So the local min occurs at -6, -1/12. Now for this next problem that we're going to do, I'm just going to kind of do it with you. To find the derivative of this problem is a little tricky. So I just want to make sure that we kind of do it together. So one of the things that we need to notice is that we're going to have to use chain rule about 3 times here, because I can rewrite this function as cosine of 2x and this quantity squared. And I like to do it that way because we can see that we're going to have to use chain rule 3 times. 1, 2, 3 times. So the derivative of the most inner function, the derivative of 2x is 2. The derivative of cosine 2x is negative sine 2x. And the derivative of cosine squared, we'd have to use power rule on this, so the 2 drops, and then we have cosine of 2x, and technically it's all raised to the first power, so I'm just going to leave it like that. So cleaning this up a little bit, I get -4 cosine 2x sine 2x. So now I'm going to find the zeros of this. So to find the zeros, I have to see when cosine 2x is equal to 0 and when sine 2x is equal to 0. Notice my domain is from 0 to pi. That prevents me from finding, just because this will happen numerous times, so this kind of prevents that, so I limited the domain. So cosine is 0 at pi over 2, 3 pi over 2, and 5 pi over 2. So then x is equal to pi over 4, 3 pi over 4, and 5 pi over 4, but 5 pi over 4 is outside of our domain. So that's outside the domain. Sine 2x, sine is 0 at 0, at pi, and at 3 pi. Which gives me x is 0, pi over 2, and 3 pi over 2. 3 pi over 2 is also out of my domain, right, because that will be greater than pi, so that's out of my domain as well. Okay, so all we have then is pi over 4, 3 pi over 4, 0, and pi over 2. It's what we are left to evaluate. And, okay, so 0 is an endpoint. Okay, so then I'm going to have, if I can put this in order, I'll have pi over 4, pi over 2, and 3 pi over 4, and of course pi, because it's an endpoint. Now if I wanted to know the absolute max and the absolute min, then I would look at pi. But since I'm only looking for local, I'm not going to evaluate the endpoints. So when I do my little sign chart, if I take a number between 0 and pi over 4, let's say pi over 8, and I put that back into the original derivative, I find that these values are negative. If I do a number between pi over 4, putting that back into the original derivative, I find that these are positive, negative, and positive. And if you don't trust me, you can use your calculator to trust my math in there. So we see that there is a local min at pi over 4. There's a local max at pi over 2. And a local min at 3 pi over 4. Okay? And if I wanted to know those exact values, of course, I would just plug them back into the original formula. So I have a local min at pi over 4, a local max at pi over 2, and a local min at 3 pi over 4. Okay, so that's for your notes for now. I want to give you just to kind of recap a little bit. What we want to remember is that when the derivative is positive, the curve is rising. When the derivative is negative, the curve is falling. And if the derivative is 0, the curve is neither, it's a possible local max or a local min. Possible, but not necessarily. We have to do a sign chart to see. Okay, so this is what I would suggest that you do. Pause the video and try these problems. The answers are on the next slide, so just pause it and try these problems. You want to take the derivative, set the derivative equal to 0, and then do a sign chart to see if it's a local max or a local min. And those are your answers. And if you have any questions, let me know. Have a great afternoon.